Okay, so the setup. We are working with underrated graphs. You heard something about that with the talk of David yesterday. So these are underrated graphs. This is my notation for the class of all underrated graphs. And I usually put something to say if I consider only graphs of size kappa or size less than kappa or something, some indication on the size when needed. And also V of G is the set of vertices of G, and E of G is the set of the edge relation, the set of edges of the graphs. So, and the main relation that we are looking at is homomorphism for graphs. So this is just a function from one graph to the other one, which preserve edges forward, okay? So it needs not to be injective, need not to preserve edges backwards, just forward. And this relation is a quasi-order, and this is what we want to study. As a quasi-order, of course, it induces an equivalence relation. And of course, you have the strict part and everything else, you know, that you can get from a quasi-order. This is my notation for that. Okay, the point is that empirical fact of life, we all know that graph homomorphism is universal in some sense or another. I mean, depending on your subject, you will surely have some theorem which says graph homomorphism is very complicated. Here is a kind of sample of things that we found in the literature from different subjects. And again, the list is clearly incomplete. So one of the strongest results I saw is from category theory, theorem saying that the category of graphs with arrows given by homomorphisms is so-called alg universal. So universal in the sense that every concrete category, concrete just means that it's category whose objects are based on sets and arrows are based on functions. So it's a technical notion, but includes most of the natural categories that we use. So every such category can be fully embedded into graph homomorphism. And fully embedded is just not a functor, it's much more than a functor. It's a functor which is fully faithful and injective also on object. So it really means that inside the category of graphs, you find a faithful copy of your original category in all possible senses, in the strongest possible way, okay? Then, of course, there are things related to orders, so more combinatorial. For example, there is a nice result saying that finite graphs are order theoretical universal, meaning that every countable order can be embedded into the partial order induced on the quotient by graph homomorphism, okay? This is a countable order, and it's universal because it embeds all other countable orders. Then this was one of my main motivation in descriptive set theory. As Yuko was explaining, there is a trend of classifying structures using methods from descriptive set theory. So if you consider countable graphs and you look at the homomorphism relation, you have natural topology on the space of countable graphs, and the relation becomes an analytic quasi-order. And Louveau and Rosdahl proved that this quasi-order is complete in the sense of analytic quasi-order. So with respect to Borel reducibility. If you don't know what it is, it doesn't matter. It's another thing showing that it's universal in the appropriate setup of descriptive set theory. And then, of course, we have all the stuff coming from computer science, so undecidability problem for the existence of homomorphism between finite graphs. And we have things from model theory saying that every theory can be interpreted in the theory of graphs and so on and so forth. This is what I meant. We all know that graphs are complicated and homomorphism is universal, right? So in every field, you have some results saying that. So what we noticed, because of certain problems that we had in mind, is that although we have all these results, each of them uses a kind of different construction, which is ad hoc for the specific result. So, for example, just to give a glimpse on what I mean, if you look at the category theoretic result, you see that it's very strong, very cute, but the point is that the construction does not need to preserve the cardinality of the graphs or of the structure. So maybe you start with the countable structures, but if the language of the structures contains infinitely many symbols with arbitrarily high arity, then the transformation given by this construction gives you a graph as an image of size continuum. So it doesn't preserve countability. Also, it doesn't allow to control simultaneously certain parameters I will speak about, like chromatic number and so on. You can control many of them, but separately. You decide your parameter and then you can control it, but what about controlling them all together at the same time? So instead, if you go to the scripted set theory side, so in particular, the first construction cannot be used in the setup of Borel reductions because there you need to transform countable structure into countable graphs. So this cannot work. If you take the other construction, which transform countable graphs in countable structures into countable graphs, okay, that now it preserves cardinality, but it's specific for Aleph 0. It doesn't work with graphs with higher size for technical reasons, and it's not functorial at all. So you cannot use it to prove, for example, the category theoretic results. This is just to say, I mean, all these constructions are somehow incompatible with each other. And for some reasons, we decided that we want to understand whether there is one construction. We know that the results are true, so there should be some kind of construction which maybe explains all of them, which gives all of them together. So a nice coding, a better coding with respect to what exists in the literature. And this is what we were looking for. And surprisingly, this coding procedure is amazingly easy. Okay, so this is why I suspect that maybe this can be known or something, but we spoke about that with many people. We've searched the literature. We couldn't find anything. But if you know some references pointing towards this kind of ideas, please let me know. So how it works. Let's step back to graphs homomorphism in the classical setting. Then we know that it is a lattice. Okay, and meet operation is just product of graphs. And the sum operation, the joint operation is disjoint sum, okay? So basically it's like in this picture on the left. You have your two graphs and you make the disjoint sum. You consider the graph and you don't add any edge between the graphs or so, such things. Of course, the point is that if you do that, even if G0 and G1 maybe are connected, you will get some disconnected graph, okay? What if you want a connected graph? If you want a connected graph, the natural thing to do is to fix some R0 and R1 on your graphs, and then you decide some length of the path that you want to join them, and then you add simply this path. So you decide the natural number L, which can be 0, but then you can make the path of length L plus 1, so it's at least 1, and you join R0 to R1. This is just the simplest connected version of the sum, okay? Okay, that's it. Basically, the idea is that we just generalize this to arbitrary family of graphs, not just two graphs, but you might start with many graphs, like a collection GA of graphs. Then you fix a point on any graphs, a vertex. Then you need a function which tells you the length of the path to connect them. Okay, so you have this function rho saying how long must be the path. And then you do the same construction. You take the disjoint union, and if the function rho says that you have to connect this graph to the other one with a path of length 5, you do that. And if it is, the only point is we use 0 for no path. So if the function rho, this is just for coding reasons. If you don't want to add a path, because this is an option, rho gives you value 0. Value 0 means don't add a path between the two, okay? That's the only coding thing, because maybe you need not to add all possible paths, you want to add just some of them. Okay, so this is the picture. So if you have, for example, 3 graphs, and the function rho says 1, 2, and 0, 1 means add the path of length 1 plus 1, so 2. 2 means add the path of length 2 plus 1, so 3. 0 means don't add any path between them. And if you have many graphs, you can get connected graphs, for example, even if you don't add all possible paths. Like in this example, this is already connected, right? So it's not a problem, not if you don't want to add the other path. Okay, that's it. This is the construction, well, with a bit of care. For the rest, I need to introduce some terminology concerning graphs, since I don't know how many of you are confident with the terminology from graph theory. I just have a glossary here of important concepts in graph theory. Well, of course, I already spoke about path. This is what you imagine. A closed path is just a path which closes up at the end, so the final point is the same as the initial point. Of course, a path can pass through vertices multiple times. If you don't allow this, you get so-called cycle. Cycle is a closed path where you don't pass through a vertex more than one time, except for starting and ending point. And then you have an important notion of odd cycle or odd closed paths, which just mean a path or a closed path or a cycle of odd length. Odd length is very important because it's the typical things that prevents the graph from being bipartite. So a graph is bipartite if and only if it doesn't contain odd cycles. Okay, so this is very important. Bipartite is what you know. Rigid. Rigid is the strongest possible version of rigidity. So a graph is called rigid not only if the only automorphism is the identity, but even more, every endomorphism, every morphism from the graph to itself must be bijective and actually an automorphism and the identity. Okay, so there are no other homomorphism endomorphism besides the identity. Okay, then we have the usual notion of distance between 2 points. If they are connected, then you have a shortest path connecting them. This is the distance, otherwise the distance is infinite. The diameter is the sup of the distance between vertices, and connected, I already used, means that all pair of vertices have a path joining them. Okay, sorry, this was very quick, but it was just to take all of you together with the next results. Okay. Here is a new definition instead. Okay, this is apparently possibly new definition, which is a little bit stronger than non-bipartite. As I said, non-bipartite means that the graph contains odd cycles. Okay. Now the problem is that if the graph is very large, maybe infinite, you might have just one single odd cycle in one place, and if you go far away from this cycle, maybe the graph is looks just bipartite. And this is what we don't want to have. Uniformly non-bipartite means that you have a natural number such that if you fix a point and you look at like a ball around of radius n, you will find some cycle inside, some odd cycle, witnessing that it's not bipartite. So in a sense, everywhere you see witnesses of the fact that it's not bipartite. And if you have that, you have a minimal number witnessing this is ng, and then you set up this parameter delta g, which is just, well, this is for technical reason, is the minimum of ng minus 2 or the diameter of g. Okay, it doesn't matter. The point is that this is well defined. Otherwise, if it is not uniformly non-bipartite, you say it's infinite, this other parameter. Okay, this looks maybe artificial, but it's very natural. For example, if you are interested just in finite graphs, if the graph is connected, this is just the same as being non-bipartite. Okay, it's the same because you have finite diameter. Even if you don't want to look at connected graphs, in the finite realm, up to homomorphic equivalence, you get that every non-bipartite finite graph is equivalent to a uniformly non-bipartite graph. Okay, so basically in finite graphs, this is the same morally of non-bipartite graphs. The point is that in infinite graphs, this is more general than that, okay, even if it doesn't not cover all possible graphs, okay? So it's some things which encloses many situations, including all graphs of finite diameter, but not really all of them, okay? It's like very large, but not everything, okay? This is the notion we use. Okay, sorry, two more things. One was mentioned yesterday in David's talks. This one was not mentioned. As I said, odd cycles plays an important role, and there is a parameter attached to that, which is the odd girth of a graph, which is the shortest length of an odd cycle, if there is some odd cycle, okay? And the girth instead is the shortest length of a cycle without restriction on the length. So the other parameter is the chromatic number. So I repeat the definition from yesterday using coloring. The chi of G, the chromatic number of G, is the minimal cardinality such that you have a proper coloring from the vertex into a set of sides, this cardinal. And proper coloring means it's a map, it's a coloring which assigns different colors to vertices which have an edge between them, okay? Why are these so important? Well, because they are the key things to check if there is a homomorphism or not. They are not the unique one, but these are the first one and most important one from the beginning, right? Because if you have a homomorphism between G and H, then the chromatic number can only increase, cannot decrease, and vice versa, the odd girth can only decrease and not increase, right? So for example, if you manage to have two graphs which have different chromatic numbers and different odd girths in the same direction, meaning that the chromatic number and the odd girth of the first are strictly below the chromatic number and the odd girth of the other one, then you know that they are incomparable, okay? Just because one parameter goes in one direction, the other parameter goes in the other one, so they prevent the two direction of the homomorphism. So let me go back to the construction of the connected sum with the paths and so on. So basically what we are doing is actually taking some graphs which are sort of labels. So this is the family HI, and you fix this family. We need that these families, these labels, are connected uniformly non-bipartite, the technical notion from before, and incompatible with each other, okay? Pairwise incomparable. Okay, now that you have them, you fix your vertex Ri to connect the things, then you can assume something more to make the construction work. You can, if you can, we demand something more for the construction. So the condition is, well, we have actually two conditions that works, okay? And for technical reasons, we need both. We use we use the first one and then we move to the other one. The first one is just that these labels have increasing coloring number, chromatic number, sorry. So since the chromatic number, especially if the graphs are finite, if the coloring number is finite, which is what we require, then you can have at most countably many labels in this way, okay? But this is a condition that works. The other, which is more generous and which works for larger classes of graphs, is just that these are all uniformly non-bipartite. So each of them has some delta, okay? And you require that this delta, which is natural number, all these deltas are uniformly bounded by the same upper bound, okay? So you take the soup, you cannot have arbitrarily high delta of the graphs. So assume that either the first one or the second one holds for your labels. Then what you do is you start with set A, you decide which of the graphs from the family are to be attached to each of them. So I is a choice function choosing the label for each element of A. You decide the length of the path to connect all these things. And then you do, this is the real object. Okay, it depends on many parameters because it depends on how you choose labels, how you choose to connect the things and so on. There are many parameters, but it's just the picture you saw before, right? It's not really complicated. Okay, this is the real connected sum that we are looking at. Okay? And what's the property? The property is that surprisingly, the construction is very simple, but if the distance rho between the various components is large enough, for example, when you are in case 2, where you have a uniform bound on the deltas, just assume that the value of rho is always above this uniform bound. Okay, so it's big compared to this uniform bound. Well, except if this is 0. 0 means no path, so this must be there. But if it is not 0, suppose that it's above this thing, then there is a sort of rigidity in the construction, because now if you take any label, Hj, and you have your connected sum on the right, then you try to build any homomorphism from this Aj to this connected sum. What happens is that there must be a unique index A, so a unique graph in the family that you use to make the sum, such that the image of the homomorphism touches this graph. So the image of the homomorphism must touch just one of these graphs, and moreover, this graph must be a copy of some label, and the label is the same graph you started with. So the label of this touched graph is exactly the same label of the graph you are trying to embed with the homomorphism. Okay, so it's very rigid. You try to throw some label, some Hij inside, and the point is that you will touch exactly something of the same form. Okay, you cannot go elsewhere. So this is very, very rigid. Moreover, if the label itself are rigid in the strong sense we saw before, then actually this is really an isomorphism, the canonical isomorphism between Hj and the component you are touching, okay? So if there is some rigidity, then it's really like an isomorphism and embedding inside the right component, a component of the same type. Okay, so the point, of course, is, the question is, are there enough rigid labels to carry out the construction? Yes, it's known that there are a lot of incompatible rigid graphs to start with. The problem is that, of course, at the beginning, these graphs have no control on chromatic number, say, or other parameters, okay? But still, you can start the construction at the very beginning with something. Now, the coding procedures actually works in this way. First of all, one just noticed that if you have any first order structure, you can code it as a colored graph. Okay, this is a bit of standard, I would say, folklore. It's just a classical technique from model theory, except that you use the coloring instead of certain more complicated construction that they use, but it's basically that construction. So we can imagine that we are trying to code a structure in a graph. You can imagine that the structure is a colored graph. Colored graph means just a graph with a non-trivial coloring in some index I, okay? Okay, so now that you have this, what you do is you make some connected sum as before, okay? In which way? Well, each node represent basically, each component in the sum represent a node in the original graph. So for each node in the original graph, you will have some component in the sum. And which component you choose? Well, you use the one given by the coloring. You have a coloring, it says, this point as color 5, and then you use the 5th label to code that. That's it. And as a length, the only point is to choose the map so that the length are large enough compared to what you have in the labels. You remember that there were 2 conditions in the previous theorem. You have to fulfill those conditions, basically, so that the construction works, okay? So this is just the thing that is written there. So this is the coding. If this is your graph, colored graph, so 4 vertices colored 0, 0, 2, and 1, what you do is you replace each node here with some label from your family H, code in the same color. So if it is 0, you use H0 and so on. And then instead of having just one single edge here, you add some long path there, long enough to make the construction work. Okay, so I mean, this is why I think it should be somewhere. Can you imagine something more simple than this? I can't, basically. Okay, so the key fact is that the rigidity that you add allows you to reconstruct homomorphism. Of course, if you have a homomorphism between colored graphs, this transfers to a homomorphism between the corresponding sums in the natural way, but also vice versa. If you have a homomorphism between the connected sums, you reconstruct a homomorphism backwards, because the connected sums are made of labels. You look at where each label is sent, okay? Each label must be sent to something of the same type, so you are also preserving the color, basically, okay? H0 must go to H0 and so on. So if you take this and transfer back, you get a label which preserves colors. This is homomorphism between colored graphs. So that's it. That's the coding procedure, and gives you like a full embedding with all nice properties, okay? So everything that you need to perform the construction is a family of labels, HI, which are connected, uniformly non-bipartite, and incomparable. And this, we know that we have many of them. And now the point is that maybe you want them to be rigid, maybe you want them to have the right cardinality, maybe you want to control further parameters. So everything boils down in finding the right labels, okay? If you have the right labels, then you know that you can perform the construction. Okay, another observation, technically speaking, as I said, we have some labels to start with. Using that, you can prove that you need this family only for 3. After that, you just need 3 labels to make the construction work. So there is a preparation using random rigid graphs from the literature. And after that, you can just use 3 labels from that point on, which makes easier to find your family, your desired family. I mean, if you want very complicated properties, it's difficult to have many incomparable things. If you just need 3, maybe you can do it. Okay. Okay. So let me move to applications. Okay, it seems too stupid to work, but somehow it works. So first application, this was one of the first things. We have this famous theorem concerning chromatic numbers and so on. So for example, there is this famous theorem of Erdős saying that for every finite value for the chromatic number, you can find a finite graph with that chromatic number and arbitrarily high odd Gert, or even arbitrarily high Gert, actually. Okay, and from this you get the same for Aleph 0 as well as a chromatic number. Okay, it's very easy. Okay. What for uncountably chromatic number? So graphs with chromatic number greater than Aleph 0. Here we have the other theorems by Erdős and Einal. If a graph has uncountably chromatic number, then actually you cannot have all possible values for GERT and .GERT. There are some constraints. This is very surprising, very strong. There must be some structure. So what they prove is that either the GERT and the odd GERT are 3, okay? So you have triangles in the graph, or otherwise you have cycles of length 4, and then the odd GERT can be I as much as you wish. So the first odd cycle can have enormous size, okay? But you have cycles of length 4. Okay, apart from this construction, this obstruction, you can do whatever you want. By Erdos-Chanel, you can do any, for any chromatic number greater than 0, you can have a graph, of course, of size at least n, otherwise the chromatic number would drop down, but a graph of size n, which has arbitrarily high odd GERT. You cannot have arbitrarily high GERT because of this constraint here, but you can have arbitrarily high odd GERT. Okay, so basically they are showing that if you fix these 3 parameters, modulo some constraint, so chromatic number, GERT, and not GERT, you have a graph in the class. Okay, the class of graphs with these properties is not empty. Okay, so more generally, let's turn this into a definition. We fix our parameters, and we construct the class of graph GNMK, where n is the desired chromatic number, m is the GERT, and k is the odd GERT. So you fix your 3 values that you would like to realize. Of course, as we saw, some of these classes are empty because of the limitation of Erdos-Chanel. All the other ones are inhabited by some graph, by Erdos-Chanel again, and these are called acceptable tripods. So the acceptable just means there is something with those characteristics. And now the question becomes, how many, you have 1, how many different graphs can you find in there? Can you find graphs with special properties, like rigid graphs? Can you have large anti-chains, descending chain? What's the structure up to homomorphism inside each of these classes? There were cases where this is known. So for example, if you have a finite chromatic number and lowest possible GERT and not GERT, like 3, then the answer is given by the categorical construction I mentioned before, for example. Or vice versa, you may demand chromatic number 3 and move the other parameters. This is given by the previous construction. But can you do the same together? I mean, move arbitrarily the 3 parameters. And yeah, this is one of the application. You fix your acceptable tripod, then either the thing is trivial, and this is trivial. For example, if you set n equal 2, then you have only bipartite graphs. Okay, so there is nothing to say. Similarly, if you set n equal m equal k equal 3, they are all equivalent for stupid reason. They contain triangles, they are tricorrelable, so everyone is homomorphically equivalent to every other one. But besides this stupid situation, what happens is that in all other cases, the class we are looking at is alg-universal. Remember, alg-universal is universal in the sense of category theory, which is the strongest possible universality result among those we saw before, okay? So this shows that these classes are enormously complicated as a class of all graphs, okay? So adding, besides the Erdos-Chanel constraints, there is nothing else that puts some regularity on the homomorphism structure on these classes. And moreover, this is a strike difference between the original construction in category theory. The full embedding witnesses this is cardinal respecting. It's not cardinal preserving because of the finite things, but the point is that if you start with finite things, you get finite graphs of different size, maybe. If you start with things which are infinite, you get things which are infinite with the same size, okay? So it's respecting in the sense that for finite things, you just respect finiteness. And for infinite things, you respect cardinality, actually. Okay, so this is as a bunch of consequences, classical consequences. For example, you can take your favorite group and prove that it is actually the group of automorphism of a graph with prescribed characteristics. So you decide your chromatic number, odd GERT and GERT, and well, every group is the automorphism group of such a graph. And every monoid is the monoid endomorphism of such a graph. Every partial order can be embedded and so on. I mean, this is one of the strongest things. So once you have this alg-universality, you recover basically all other things. Yeah. So what's the key ingredient? We already saw that the construction is stupid. The point is finding labels, okay? Once you have the labels, the construction just works. And here what we need to take into account is that the final graphs you are constructing are certain connected sums of graphs, okay? And you want these connected sums to have a certain chromatic number, a certain girth, a certain odd girth. So how do you compute these parameters on a connected sum? Well, the construction is so smooth that basically the chromatic number is just the soup of the chromatic numbers of the labels, okay, as small as it can be. The girth is the minimum of the girth of the labels, and the odd girth is the minimum of the odd girth of the labels. So basically, the construction doesn't change these parameters. What you have in the labels is what you will find in the big graphs. The big graph doesn't add anything to the how much complicated is the coding. Okay, so all you need to find is labels which fulfill your desired parameters as for chromatic number, girth, and odd girth. And this is the technical theorem behind the previous one. If you take an acceptable triple, supposing that you are not in the stupid situation where everything is homomorphically equivalent to everything else, then you fix your cardinal and you have enough labels. Okay, so you can construct families. If lambda is infinite, you can find family of size 2 to the lambda. If lambda is finite, you can find infinitely many, but just countably many, of course, things. So, I mean, the maximal number that you can imagine, there are no more structure of that size. So you can find family of labels of maximal size in the class, which fulfill all the characteristics. So in particular, they are incomparable, connected, uniformly non-bipartite. This is the background for making the construction work. And moreover, because of the application, the diameter, well, this is not because it's extra feature, the diameter is bounded, but they respect the cardinality that you want to preserve, and they have the desired chromatic number, girth, and odd girth. So if you use these labels, you are done. And the point is, how do you construct these labels? Do we need really a new machinery? No. We use the connected sum again. Okay, there is a strange bootstrap in the proofs, basically. You set up the construction, you start performing the construction with stupid graphs from the literature, not stupid, but I mean, without any possible control on them. And building on that, you use the result to bootstrap and build other things, and you bootstrap and you end up with this construction here. So basically, I'm really saying that all the proofs rely on the connected sum. There is nothing else. It's just bootstrapping this and improving the characteristics of your graphs. Okay, so for example, the fact that we get a cardinal respecting things, in contrast with the classical construction from category theory, means that, for example, the same thing can be used for proving things in descriptive set theory. So to prove that the homomorphism relation on countable graphs is complete with respect to all analytic quasi-order, with the extra feature that now you can restrict your homomorphism to the class with that chromatic number, that girth, that odd girth. The original construction by Luca Motto Ros was using arbitrarily large cliques. So the chromatic number was Aleph 0, and the girth and odd girth were 3, the minimal possible value. And you can not move that. I mean, you have these cliques inside, so you cannot do that. With this construction instead, you can control these extra parameters for free. I mean, it's in the construction itself. Also, we were also concerned to lift in these two uncountable graphs. As Yuko was explaining yesterday, there is this generalized descriptive set theory that can be used to study uncountable structures. So you move to this uncountable setting to study uncountable graphs. You try to take the result by Luca Ros, and this simply doesn't work. Okay, cannot work in any possible sense unless kappa is a fixed point of the Aleph function, which is regular, unless kappa has some certain things. But if kappa is Aleph 1, it cannot work. Okay, our construction is just like water. I mean, you give me your size, and I perform my construction, and you get the results for uncountable graphs as well. So this is the same as before, but in the uncountable setting for regular cardinals satisfying usual conditioning generalized descriptive set theory. And again, the construction is just the same. And then you can go on. So here I have a quick list of many other things that I don't want to talk about. The paper is rather long because we are finding new and new application. And if you have other ideas, we can discuss them. But for example, you have things like in model theory, you can embed any theory in the theory of graphs, but can you do the same with graphs with certain chromatic number or things like that? Yes, of course, you can do now. With this construction, you have model theoretic interpretation inside the class of graphs with desired parameters. You have undecidability results for computer science, even in strange contexts I don't want to mention. Actually, this was this was one of the starting point from us. It was master thesis of Scamperti, who went to Prague and was given this problem of certain decidability in so-called logic with atoms of the graph homomorphism, something like that. So this was one of the motivation. We had to develop this. Also, it's not just about the chromatic number or these kind of things. There are many variations of this concept. Some of them were mentioned by David yesterday. Some other are this circular chromatic number, fractional chromatic number, and things like that. And I don't want to enter in details, but these are well studied. Okay, and then you can play with this as well. I mean, basically, you do the same construction. I mean, there is some work, of course, in building everything, but the construction is so flexible that can be easily adapted to all these other contexts. So if you want to have a certain circular chromatic number, I don't know, like 3/2 or something, some fractional value, then you can do that. You can build your graphs with that characteristics. Okay, I want to mention one or two, depending on how long it takes, applications which are totally outside our original scope. Our original motivation was these undecidability results plus the descriptive set theory stuff. I'm a descriptive set theory, so I was aiming to that, okay? But then we realized, okay, let's try to do some more combinatorics. Let's see if we can say something apparently new, apparently because maybe someone will raise the hand and say, well, this is in a paper by Erdos, then this kills everything. But anyway, I think that the method of proofs is in any case valuable because it's simple and works in so many situations. So what's the first application, combinatorial application I have in mind? So people studied this class of graphs where you forbid certain graphs to appear in the class, okay? So what you do, you take a class of graphs that you want to forbid and look at all graphs such that none of the forbidden graphs can be homomorphically embedded into your graph. Okay, so you want to avoid to see inside your graphs those forbidden graphs. Okay, and this class F is fairly arbitrary in the problem. Okay, you can take your family and say, I want to avoid these graphs. Okay, this is considered quite important. As I learned, I'm not saying that it is important for me, but we learned that it's quite important. So the point is to study this class. This class is downward closed. It's closed under product sum, so it's so-called an ideal in the structure of graphs. Okay, and one of the best results that we found in the literature, unless we missed something, is a result by Nejetril and Rod. They are master of this kind of stuff. That say if the class for F, forbidding the graphs in F, is non-trivial, then you can find an infinite set of incomparable graphs, okay, even finite, which is very strong because it says, okay, you have already large anti-chains. But of course, now we have the taste of doing more. So can we, for example, find rigid graphs inside this forbidden F? Can we have larger anti-chains? Can we have descending chains? What's the structure of this for F? Okay, can we have more than just one infinite anti-chain? And the point is that, okay, you realize, well, this was, of course, in the original thing. What I mean by trivial is that if you have the one-point graph, you cannot avoid it, okay? So the class is empty. So this is the first trivial situation. Then the other situation are the following. Suppose that you want to forbid a class which doesn't contain the one point, otherwise it's empty. Then there are two stupid situations which are, if for F consists of if F contains at least one bipartite graph, then to avoid the bipartite graph, you need to be discrete, so no edges, okay? So this is the first situation. The other situation, which is a little bit more subtle and was not noticed, is if your class contains odd cycles, but with arbitrarily large length, okay, so odd cycle arbitrarily large, then again the class is quite simple because it consists of all bipartite graphs. If you want to avoid all cycle at once, then you must be at bipartite, okay? Because if you're not bipartite, you must contain some cycle. So that's the trivial thing. Well, surprisingly, apart from that, you have a complicated class. complicated in the strongest possible sense. So if F is not in one of the two easy situations, then it is again alge universal. So universal in the category theory setting, so it's the strongest possible universality. So you will have rigid graphs, you will have all those properties, you have large anti-chains, descending chain, and everything else inside your forbidden class. Not just one anti-chain, but everything you want. Okay? So this is pretty strong, I guess, and apparently new. Okay, I have time for the second application. Yes, I'm glad, because then I can mention also some work from Vienna. Okay, there is another trend, for example, so this is a completely different line, well, not completely, but different line of application in combinatorics, which is about study uncountably chromatic graphs. This is important because you saw the theorem of Erdos-Scheinal. If the chromatic number is uncountable, then there are some constraints. For example, you cannot have arbitrarily GERD and odd GERD, okay? And there are certain constraints that you need to have. So it's very important to understand whether an uncountably chromatic graph must contain certain graphs, okay? So it's a kind of structures about these objects. So the theorem by Erdos-Scheinal, the ones I mentioned before, follows from this kind of idea. If you take any graph with an uncountably chromatic number, then it must contain a subgraph, not an induced subgraph, just a subgraph, which is the complete bipartite graph where you have one side with just J elements, finite J, but arbitrarily high J, and Aleph1, many elements of the other one. So complete means you have a bipartite graph and you have all possible edges between the two parts. One part is of size J, finite number, but you can choose your number. The other part is size Aleph1, okay? And if you have a graph with uncountably chromatic number, for each J, for each finite number, you will find a subgraph of this form there. Okay, so it's very strong structural result. And there was a linear observation of this form. For example, Heinal Komiat proved that not only must contain these graphs, but also other kind of bipartite graphs that I don't have the time to draw on the blackboard, but if someone asks afterwards, I can draw a quick picture. So this is a kind of bipartite graph, which is important. And again, it must appear in every graph with uncountably chromatic number. And then there was this result by Heinal Komiat saying that, assuming the continuum hypothesis, so far it was ZFC always. Okay, now assuming some extra hypothesis, you can have a triangle-free graph, so a graph without triangles, which is something desirable in the theory, of size the continuums, which have chromatic number Aleph1, so uncountable, and omits the graph H omega, omega plus 2. So these are in contrast. This one must appear. The plus 2, which as you can guess is a minor variation of this where you add one vertex, instead can be avoided. Okay, it can be avoided. So it's there on the border. Okay, but it's under CH. And this is quite old. Everything, all the results I'm mentioning by Erdos, of course, are very old, but and here is a big upshot. Daniel Sukup, after 30 years, actually, so it took a long way to go there with a different construction, show that you can have this last theorem without the continuum hypothesis. So just in ZFC, you can prove the same. You can have examples of graphs with chromatic number Aleph1, which are triangle-free, and they omit this strange graph, the +1 version of the previous thing. So this is a ZFC result. So we got interested in this as well, and we asked, okay, now we have one example. How many examples can we have? Do we have anti-chains? Do we have rigid graphs? Do we have, which kind of examples can we find? Is just one curious things in life, or it's more general? And of course, as you can expect, you employ our method with a little bit more work, and you show that this category as well is alge universal. Universal in sense of category sense. So not only you have one example, but you have as many examples as you wish, and you can add certain constraints, you can add rigidity, you can have large anti-chain, I mean, you can do whatever you want, even inside this strange class with just one example. Okay, now there's more than one example, of course. Okay. So in particular, there is not just one graph of the size, but there are 2 to the 2 to the Aleph0, many graphs of that size, and you can ask that they are rigid, and you can ask whatever you want. Okay, so I think this is again another fairly strong application. Omega, oh, I actually don't know, but if you can omit that, you omit all the other ones. Now you have to change the question, right? Because omega plus 2 is a subgraph of omega plus 3. So if you must contain omega plus 3, you contain also the other one. I mean, so this is a border, but there are variations of this that can be considered. Okay. Oh, I had also a third application. Do I have time? Yes, I will be very quick. A third application, even this one is very recent. This comes from a results of Negetril that was never published and appeared only recently, like 4 years ago, in a paper with the other co-authors, like with Ubicka, Fiala, and Long. And this is a sort of fractal property of the graph homomorphism structure. What do I mean? Okay, you take two graphs, G1 and G2, provided they are not the complete graphs of sites 1 and 2, okay, in which case there is nothing in between. But if you are not in this case, then you can consider the interval of all graphs between the two, okay? And this interval is non-empty if you are not in the study situation. And again, the point is, how much complicated is each of these intervals? You have an interval. Are there intervals which are linear, for example, or easy with few elements and so on? And the answer is, again, no. If you have two finite connected graphs, which are not the easy case, then, again, the interval is universal. So you can do whatever you want inside that interval. So it means that it's very dense, it's very fractal, meaning that in each place you go to a very small part and you can embed everything inside this small part. No matter which graph you choose, there is only one point here, is that these graphs must be connected. In particular, G2 must be connected. And actually, well, we have a control on what happens if the graphs are not non-connected. I don't know if it is mentioned later. Otherwise, I will not say anything else. Moreover, since the construction, our construction is very flexible, you can not only is algebra universal, which is already new because the result by Negetril and the other ones was not a categorical embedding, was a way more weak embedding, form of embedding. This is a stronger result. But also for free, you can control GERD, and so on, okay? Besides obvious limitation, because you are in between G1 and G2, so I mean, you have some constraints which comes from G1 and G2, but everything else, everything acceptable can be realized for free. Yeah, it's the next slide. So what about the connectedness? It is not possible to do the same with graphs which are disconnected, provably, but what we can do is just, okay, characterize what you can do. So we have a neat characterization on when you have the fractal property or not for non-necessarily connected graphs. So suppose that you have your interval here. Now suppose that G1 and G2 are finite but not necessarily connected, okay? What happens is that the structure between the two is universal in the usual sense of this talk, if and only if there is at least one rigid graph in the interval, if and only if there is some technical condition on the connected components of the two graphs, which must be satisfied. So we have a certain technical condition, which is very easy to verify. If this holds, then the interval is universal. If this doesn't hold, not only the interval is not universal, but it doesn't contain even rigid graphs or so on. So it needs to be somehow simple for some reason. Okay, so it's again a kind of dichotomy. And this is my final comment. In all applications, which are much more than this actually, you see that there is a kind of, every result is a kind of dichotomy, basically, okay? So we start usually with some class of graphs. All the class of graphs which work in the application are closed under quite large connected sums, because otherwise we cannot use our construction. Our construction is based on connected sums. So if the class doesn't contain large connected sums, you can just not perform the construction. But all classes we mentioned are closed under this, this thing. Assume also that your graphs are uniformly non-bipartite. This is a technical condition we would like to remove, but we can't, okay? But it's very large. I mean, it's not that bad. It's a quite natural thing. Then what happens is that either you have just very small anti-chain, size 2, or if you have at least 3 incomparable graphs in your class, then you can already perform a weak embedding. This is the weak embedding of Negetril and the other authors. So you have something preserving the homomorphism, okay? Not a categorical embedding, but some weaker form. And this happens just if you have 3 different graphs, okay, 3 incomparable graphs. Moreover, these 3 incomparable graphs can be taken to be finite, which happens sometimes, then you can also respect cardinalities. So you remove some difficulties from the previous construction. And this means that the order of the collection of finite graphs in your class is universal in the sense of orders, okay, and many other applications. And if you can find 3 rigid graphs now, so a bit more, if you find 3 graphs incomparable but now rigid, then actually you get the stronger version, the strong category embedding stuff, okay? So basically, either the structure is very simple with poor anti-chains, or the structure is as complicated as possible. And of course, this is just a meta-theorem because, I mean, of course, it's a meta-theorem, but I show you already some hopefully interesting application, and there are much more than that. Thank you for your attention.
Okay, if not, yeah, there is a question.
I was waiting for this question. I said that. I mean, you were not paying attention. I said, if someone asks, I will draw a picture. It's a kind of bipartite graph which is very simple. Okay, basically it's built in this way. You have an infinite set of vertices. Call them x0, x1, and so on. Okay. Then you have a second copy of this. Call them y0, y1, y2, and so on. Okay. So h omega omega, okay, not with the +1, is this is a bipartite graph, okay, and you just connect each of these to all the other ones from its level on. So this one is connected to everyone, okay. The second one is connected to this one and the one above, but not to y0. The next one is connected to y2, but not to y1 and y0 and all the ones above, and so on. So it's very close. It's not complete, okay, because each of these vertex is missing something, and each of these vertex is missing finitely many objects here. Each of these vertex is missing infinitely many objects on the other side. Okay, it's not complete, but it has many, many edges. So this is h omega plus omega. If you want to do the +1, what you do is you add some z, which I put here, but should be rather on this side. But you put here because you just connect it to all x's, and that's it. This is the +1, h omega comma omega +1. And as you can imagine, the +2 is add the z prime and connect it to all of them. So I think it's very shocking, the fact that if you just add one z, then you must contain that. Every uncountably chromatic graph contains something like this. If you add a second z, you can omit it. I think the combination is fairly a strong result. Thanks for the question.
Other questions? Yes, go ahead. Yeah, please. Yes.
Okay, I don't know, because the point is that we are working in the opposite direction. We are not trying to find something which has some universal property with respect to the graph homomorphism, like a universal thing which must contain all of them, for example. We are embedding inside certain complicated things. So this doesn't add any information at all on results which aims at a different direction, like universal things. Yes, because they are algebraic universal. So you can embed them. The point is that you don't know where you will embed this. I mean, you know that you can control some parameters from graph theory. From the graph theoretic point of view, is interesting this. But you can embed algebraic universal means you take your favorite class of structures, no matter the language, no matter what are they, you can embed this class of structures into graph homomorphism with extra features.
All right, then let's thank Luca again. We have a short coffee break and we resume at 10:45.